a brief introduction of Bihan. So Bihan is a Nanyang assistant professor at Nanyang Technological University. He received his PhD degree in electrical and computer engineering from University of Illinois at Urbana-Champaign in 2018. So his research interests span areas of machine learning, inverse problems, and applications in image and video processing, computer vision, security, and computational imaging. So he is an elected member of the IEEE Computational Imaging Technical Committee. He was the recipient of 2016 Yi Fellowship and 2012 Professional Engineers Board Gold Medal in Singapore. So he also received several paper awards, including top 10% Best Paper Award at ICIP 2014 and the Best Paper Runner-Up at the ICME 2020. So his talk for today is From Signal Processing to Machine Learning, How Old Ways Can Join the New. Without further ado, let me turn the mic to Bihan.
All right. Thank you, Jane. Thank you. And thanks to all the audience for joining our webinar today. Okay, let me share my screen now. Okay, can you all see the screen I have, the slides?
Yeah.
All right. Yeah, so I mean, thank you all for coming to the webinar today. So my name is Bihan Wen. So I'm from Nanyang Technological University, NTU, in Singapore. Today, I would like to share with you some of my experience and recent research, which which kind of witnessed the evolution of various deep data models from all the way from signal processing to machine learnings, and also want to share some of my experience, like how we can kind of reconcile those older machine learning methods to and with the so-called modern deep learning methods, and demonstrate some kind of advantage and benefits. All right. So just a quick kind of introduction for my background. So my team and I working on machine learning, we work on all sorts of learning techniques ranging from more rigorous optimization problems to the recent deep learning methods. And of course, we look at signal processing problems like denoising or super resolution, deblurring, and also, of course, I'm part of the computational imaging TC. So we are working on computational imaging problems such as magnetic resonance imaging and also synthetic aperture radar imaging, or a type of inverse problems. And also we work on computer vision. So actually, many of the signal processing and computational imaging problems which we are working on actually belong to inverse problems. So I know some of the audience are actually students. So for those of you who are not familiar with inverse problems, I just give some examples, right? For example, denoising, which aims to estimate the clean image from a noisy measurement. This process is called denoising, right? Another example is so-called super resolution, which aims to estimate the high resolutional image from a low resolutional measurements. Okay, so these are just some examples of inverse problems, but all the inverse problems have something in common. So if we kind of call this measurement as y, and the images we're trying to estimate as x, so for the linear inverse problems, x and y will satisfy this linear relationship. That is, your y will equals to a, which is a system matrix, times x plus a noise e. And the only difference is that for different problems, the a and the e will be different. For example, for denoising, if it's additive noise removal problems, your A will be identity matrix, and your E will depend on your actual noise distribution. For super resolution, your A will be your decimation matrix, which is pretty much a low pass filtering plus a downsampling operator. And of course, besides image processing, well, lots of imaging problems are also inverse problems. One example, our team is working on is magnetic resonance imaging, MRI, which aims to kind of image for example, your brain using your MRI scanning machine. And the machine actually measures some kind of a frequency response measurements, but no longer in image domain. This is actually in the K space, in the frequency domain. And of course, for these inverse problems, we your A matrix will be your FU, which is a DFT followed by a downsampling operators. And here your X is your MRI image, your Y is called the K-space measurement. And this problem is actually not easy because you will get much fewer measurements in the K-space comparing to your image dimensionalities. Normally, your measurement will be much lower dimensional comparing to your image size. So that, well, the inversion will not be quite obvious. Instead, you will need some smart tricks or smart algorithms to come up with a high quality image reconstruction. So that we need a kind of a good image reconstruction algorithm to go back from K-space to image space. But how exactly can we do this? We can actually trace back all the way to the classic compressed sensing theory, where sparsity plays a big role here, because people believe that the image, the underlying image, will not be some random signals. The so-called the ground truth or the underlying image has to satisfy this transform domain sparsity. But of course, for classic compressed sensing, the transforms are just classic transforms. There's no learning involved. Some of the famous transforms like DCT, wavelets, those are, all of them are good sparsifying transform. And of course, if you bring in this linear imaging constraint, you can always form this fidelity term such that in your loss function, your sparsity term will becomes a regularizer for the whole loss function, for the whole optimization problems. Okay, and actually recently, actually together with Sai and my PhD advisor, Johan Bresser and Luke, we wrote a paper on, surveying some of the recent MRI reconstruction algorithms, and we kind of list a timeline and want to see how the MRI reconstruction algorithm evolve from, 2000 and all the way to the recent deep learning methods. And the interesting thing is, in fact, the imaging system is the same, but the only thing evolved is actually the underlying data models. We can see that in the in the 2000 time, most methods use signal processing tools to model the underlying image, whereas more recently people look at how machine learning can help to come up with a more effective image model. So in fact, the evolution of the MRI reconstruction algorithm is the evolution of the data model. So that actually brings us the kind of a topic like how we can actually kind of analyze the pros and cons by having this evolution of from signal processing to machine learning. Okay, but I mean, but the problem is like, why do we need a data model? I mean, how the data model can help to come up with a better reconstruction algorithm? To answer this question, it actually brings me back to the very first question I asked myself when I did my PhD. That is, if I give you two images, right, like a noise plus maybe another one is natural images, what actually make this image look like a real image? So what are the patterns that can distinguish from the natural images from something else, from corruption, from noise? Our human eye are really it's very easy for us. Like we can immediately tell that image on the right are definitely natural image, but for a computer, for an algorithm is not quite obvious. You actually need some mathematical rule to make a decision, and this is actually a data model we're talking about. Where we need actually a mathematic data model to solve such problem. And it turns out that people like to use machine learning to exploit the data model nowadays, and there are many machine learning approach to do that. Ranging from the classic Gaussian mixture models, PCA, and all the way to the recent deep learning methods. Even though I don't like it, but people kind of categorize different learning methods in terms of shallow method and deep methods. I mean, in principle, the only difference is that if you view this method as a neural networks, and if the hidden layers number is more than one, and people call that deep methods. It's very straightforward way to categorize the old method and new methods. People want things to be deep. But having this kind of a machine learning method, you can do all sorts of applications for images, such as ranging from computational imaging all the way to computer vision, high-level computer vision problems. All of them will need a way to exploit the corresponding image models. But no matter what you are doing, the most important thing is what is the data model you are talking about? How can you come up with the right way to model the images you are interested of? That's the key problem for all of these kind of applications, for all kind of machine learning methods. And why people believe that machine learning is kind of useful for exploit data model is mainly because that people believe a data-driven model can be more effective than most of the analytical models. So for when we say analytic models, we're referring to all sorts of signal processing tools like non-local mean, for example, total variations, and also sparsity, which is very classic tools we're using. But analytical model referring to the sparsity over those fixed transforms or fixed dictionaries like discrete cosine transform or wavelets. And actually, I want to use the sparsity as one example to show, how we can actually, starting by some classic sparsity and all the way to make it like a data-driven approach. Okay. So for those of you who are not familiar with sparsity, let me just quickly give you an idea. When we say signal is sparse, it's nothing but it means that most of the coefficients of the signals are zero, right? It's very simple concept. But of course, we are not only talking about the signals that are sparse in the spatial domain or in the signal domain. In fact, a dense signal can also be made sparse in certain transform domain. Very simple example is the sinusoid signals where, well, by looking at the signal itself, this is a dense signal, but we all learned this in the college that sinusoids can be made sparse in the discrete Fourier transform. Another example is the DCT, discrete cosine transform, which people commonly use for image processing. And in fact, as you can see here, for natural images, they can be made highly sparse in the transform domain. And this example shows that we can actually represent a natural image using the DCT transform, and in fact, the coefficients will be only few of them are non-zeros. Most of them are kind of close or equal to zero. But this is not true for noise or some other corruptions. In fact, if you're talking about IID white Gaussian noise, it's still in the transform domain, it will be still like something like IID white Gaussian. So this actually tells you a good feature representation that you can use it to distinguish your natural images from noise, from other things you're kind of try to kind of remove or try to differentiate from. So by having these observations, we can actually do something interesting to those noisy images. I just take a example like cameraman images corrupted by noise, and if you simply apply your DCT to this noise image, the clean part, the underlying image will be highly sparse, something like this, lots of zeros, only a few non-zeros, whereas your noise will becomes like a noise in the transform domain. And this one give you a way to kind of decouple or kind of decouple the clean image from the noise, so that your noise will becomes the noise in the spatial domain, but those kind of sparse pattern will get to the denoised image or denoise estimate by having this transform analysis. And this is actually one of the simplest denoising scheme you can have. It's already performed the job, right? The denoising is done for this case. So this simple example shows you like how the power of sparsity and the power of the signal processing tool, what they can do to deal with some of the signal processing problems. So well, then the problem is like, so is this transform or analytical transform already good enough? Well, it turns out that we can do something better than them. And what we were trying to do is we're trying to introduce some of the machine learning ingredient to make this transform even better, right? But the question is, how can machine learning help to further improve the transform in terms of sparsity? Okay, so here I can show you the same example as the image representation here. So as we show that by applying a DCT, which is an analytical transform, no machine learning involved, it already gives you something pretty sparse. But by having a learn transform or introduce a transform learning ingredient there, we can even make the feature even sparser comparing to analytical transform. so this is actually something, I'm working on for my PhD, and this is, together with Sai, and actually Sai introduced the very first concept of transform learning. But, I also spend many times come up with different form of transform learning just to make the representation even sparser. Okay, so just show you some of the thing we did. So we try to learn the union of transform instead of one, so that we may be able to handle even more complicated images with very diverse structures or features. And also, we also try, like, can we learn the tree structure of a transform, so that this kind of a transform trees can handle those data with even flipping and rotation properties in a better way. And we also made online version of transform learning, so that this kind of online transform learning can handle those spatial temporal data, where your data will not kind of be ready at the same time, but maybe arrive sequentially, something like videos or your surveillance camera. And last but not least, we also try to combine transform with some other properties, like low rankness or those non-local properties, to come up with a more effective way of, say, restoring or modeling images. So in terms of that, this kind of learning concept in the transform works pretty well. I just show you some examples, starting by image denoising, which probably the simplest inverse problem we can have. So we're considering a noisy image where, let's say, we just use IID Gaussian noise as an example. So like I illustrated, having a sparsifying transform can help you to distinguish your clean image from noise. And having transform learning such that having transform learning can help us to denoise the image to come up with a noise-free estimate. And because this learned transform can give you a much sparser representation comparing to an analytical transform, such as DCT, of course, for denoising, we can get a better result. So here's actually a comparison for denoise estimate comparing to the result using transform learning and the DCT transform. And we can see that we can actually got more than 1 dB improvement than the DCT result, and we get rid of lots of artifacts here. So not only in transform-based method, in fact, the transform learning algorithm can do even better than some other denoising methods, such as the famous BM3D or EPIL, because of this machine learning kind of powerful ingredient here. Another example is the video denoising. So recall that we have an online version of transform learning, which is really good at handling spatial temporal data. And video is one of such examples where you will have some data which are not static, but the data is keep changing from frame to frame. So for that case, when trying to restore a noisy video like this, we're trying to estimate what is the clean version, right? So at the time, we actually did pretty well. We can outperform the state of the art, which we call that VBM40. Well, if you are familiar with VBM3D, BM3D, VBM40 is actually a video version of that, where they are doing a window filtering over not 3D patches but 4D patches. So even with that, you still observe some artifacts like locally for some places, and our method will be leads to a much better quality in terms of, say, local feature preservation. And if you look at those restored patches, apparently there are more structures and meaningful features has been preserved comparing to VBM40. And all of these are due to this kind of a learning, and learning can help you to adapt your transform to those video frames or video patches in a very like online fashion. And this is actually due to this adaptivity. Okay, so machine learning is actually kind of evolving from like old times to recently. And actually, if you look at 1990s, right, there are already some classic machine learning tools like GMM or decision trees. And during the time when I did my PhD, the popular kind of tools are like dictionary learnings or low rankness. Those are like the one in the kind of 2000. And of course, more recently, people look at deep methods like convolutional neural networks, generative adversarial networks, and RNN. And for those which involve more than one hidden layers or maybe more layers, people call that deep learning. And this turns out to be the most popular tools recently. And I mean, why people love that? I mean, the reason is also kind of simple because nowadays we have more data, right? You have more number of data, and it turns out that deep learning scales better. They can actually give you, proportionally increasing performance as your amount of data increases. But on the contrary, the older or like a shallow type of learning algorithm doesn't really work in that way. They pretty much saturate it when your amount of data is increasing. That actually brings us the big gap when we are talking about big data applications. So by understanding this, we were trying to see if we can actually make some of the shallow methods, such as transform learning or like a dictionary learning, sparse coding, to a little bit deeper. Can we make the architecture deeper? I mean, the reason why we want to do that is because there are lots of advantages if we have a deep model. I mean, here are at least three advantages which I think are most important. I mean, for example, the deep model comparing to a shallow type of transform learning or dictionary learning, they can definitely give you some improved performance if you have sufficient amount of training data. And actually, deep model can actually get rid of those hyperparameter tuning issues, which normally will be a big problems for those kind of optimization-based methods. You have to deal with those hyperparameters. And another important feature for deep learning is that it can give you an end-to-end optimization approach to come up with a model which directly serve for your ultimate task or ultimate objective. Whereas for like optimization-based method like transform learning or dictionary learning, normally we have to use a proxy in the loss instead of the true loss we actually want to look at eventually. So these are some of the advantages to kind of drive us to kind of make this shallow method deeper, right? And there are actually some way to do that. We tried, try to actually do this. The first step we did is that we tried to unroll a sparse coding method. I mean, the very famous ISTA algorithms, which kind of do this sparse coding in an iterative way. And then later, there's so-called learned ISTA, which can unfold the iterative algorithm to be a feed-forward network, so that you can actually enrich your model flexibility and make the whole model more scalable. So we actually did a kind of applications on super resolution by using this learned ISTA idea. And comparing to the baseline, which people normally use bicubic interpolation to upscale image. And this is actually the result the baseline can get, whereas the details somehow are blurred due to this interpolation process. On the contrary, by having this kind of learn ISTA idea, which is a deep version for synthetic sparse coding, we can actually get much sharper details and much more information by looking at high resolution or super resolved image. So we actually proposed this around like 2015 or to 2016, roughly around the same time as the very famous SRCN. But unfortunately, we cannot promote this idea from a signal processing perspective, and it seems like people are more, kind of familiar with the deep learning approach. So, but in fact, we can actually do slightly better than SRCN. Whereas, I mean, I think people are actually more familiar with SRCN in around that time. But this is actually the first step we try to make a shallow method deeper by using unrolled network. And later we also look at how we can unroll maybe a transform learning method to kind of super resolve or do a data fusion for not a single image but a multi-spectrum image. This is a joint work with folks from MERL, Mitsubishi Electric Research Lab, including like Ulak Beg, De Hong, and Petros Hassan. At the time, when we come up with this idea, is that we want to kind of unroll the transform learning idea so that this kind of transform will not become a single transform. Eventually, it will become like multi-layer structures, which is something similar to deep neural networks. So this is what we do, and it turns out that this also works pretty well for remote sensing applications. Where here I show like one examples where we try to super resolve like a hyperspectrum image, which is try to image the Bay Areas in California. And this is what you get if you are directly using a bicubic interpolation to upsample the image for 4 times. then you couldn't get too much details for those buildings and roads. But by applying this learned, unrolled, transform learning ideas, which we call that deep cast, you can actually get much more details. But all of these improvements are not from a single image. They can be coming from other spectrums or other channels as well, because this kind of models can actually fuse different channels to kind of super resolve the target channels by using a multi-layer structure like this. So just want to show you that there could be some benefit by kind of making the shallow method deeper, right? By enjoining more scalable models. But meanwhile, we also want to ask, is there any drawback of deep learning? Because there's no kind of free lunch. There should be there's still some problems for deep learning in practice. And here I just want to share with you some kind of problems we kind of encountered in the research. The very first problem is that we realize, sometimes deep learning can be fragile, not quite robust. So we kind of study these problems when we actually try to train or come up with a classifier over images which are not quite clean, but maybe images with some noise. I mean, this is actually quite common if you're talking about images you captured from real life. There will always be some corruptions, either noise or blurry, right? Even though there are lots of so-called state-of-the-art classifier reported when people run over, say, ImageNet or those kind of baseline or benchmarking data set. In fact, if we're no longer running over clean images, but if we're running over noisy images, we observe that the performance, the classification accuracy will actually drop dramatically as we gradually increase or inject more noise to the images. So this is actually a big problem because can you say that a noisy cat is no longer a cat? Definitely not. In fact, if you really want to deploy AI or machine learning tools in the real life, you have to make sure that your model is robust enough and should be kind of should be able to handle those images with non-idealness. So this is actually explaining some of the problems, like you normally see some reports on, crashes of those kind of autonomous vehicles, because the kind of the data you're handling is no longer the data from your training set, right? And also, even if you deploy some state-of-the-art detector in real life, they may give you some really stupid answers, like they recognize a turtle as rifle. And not mentioning some of the adversarial attacks, people can even train patterns which can defeat some of the detectors. Like they can even like some kind of camouflage, which totally disable the kind of the person detector here. So all of these are due to the kind of the vulnerability of deep models. And actually, this is one of the problems by having this generic models without a particular priors or structures, unlike the classic machine learning or classic signal processing. So this is one problem we figure out. And the other problem is that it turns out that deep learning may not always wins comparing to classic methods. I take the example of the compressed sensing MRI as one of the applications we kind of work for many years. So recently, there are many methods apply deep learning to reconstruct MRI images from compressed sense measurement in K-space. One of the examples is the so-called is a famous ADMM-net method, which did pretty good job for data in general. But we do realize, I mean, it's better than some of the previous methods, like the DLMI method, which Tsai invented around 2013. But in fact, by not using deep methods, instead by only using a shallow transform learning method, we can actually do better than those deep methods. And actually, here the reason is we are actually not talking about image in general, but we're talking about images for special modalities or very specific imaging forms, so that somehow your method should be aware of this imaging modalities or domain specific priors. But this is really hard for deep method because it tends to be more generic. So that for this kind of applications, maybe you should kind of think twice when you want to go directly to the deep learning kind of area. So just want to summarize, what are the pros and cons I myself consider, or when I want to ask myself if I want to choose deep learning. These are some kind of pros and cons I probably want to share. Um, so first, I mean, this is without doubt, deep learning has multiple free layers comparing to like a shallow method, which probably only have one free layers. And this necessarily means that deep learning kind of approaches or models are more flexible and actually more scalable. I think this is actually definitely one of the advantage for deep models comparing to shallow methods. And the second thing is we have to look at whether this method is supervised or unsupervised. But I know recently deep learning community also look at self-supervised learning or unsupervised learning. But I have to say, like, still majority of those deep models are still supervised. You have to kind of prepare a corpus for training. And sometimes, especially for those applications which you don't have easy access to a large corpus, have kind of a training over a big corpus will be something like a data inefficient way of training. So this is like some potential drawback for deep learning methods. But on the contrary, many of the conventional methods are unsupervised, such as most of the signal processing tools or even the transform learning methods we kind of work on. They can made completely unsupervised, so that you don't have to prepare a training corpus. And in this way, this method will be more data efficient in such case. And the last point I want to share is that even though deep learning tends to be more generic, like there's very few assumptions made by the model, and it's almost a free model. But sometimes you actually want to have some prior embedded in your model. And especially for like the imaging problem I just shared, or maybe if you want to handle some images with very specific modalities, like or specific styles, probably you have some understanding of the data, or you have some understanding of the physics of the imaging process, such that you want to use those kind of prior by make some assumptions for your model. And those one can necessarily lead to some regularizers or structure of the model. And for conventional approaches, it's actually much easier to embed those structures comparing to deep learning approaches. I consider this as one of the potential advantages for conventional approaches if you are dealing with such type of problems. So these are just some kind of pro and cons, and I think normally I kind of bear this in mind when I want to kind of choose the right strategy to tackle specific problems. But actually, but besides understanding the pro and cons, the last topic or last point I want to make in this talk is that sometimes we also want to kind of reconcile the signal processing and deep learning so that we may enjoy the benefit from both sides. And actually to do that, we have to kind of revisit those kind of old methods or signal processing method and see how they can help us to improve some of the deep learning method, so that old ways can join the new, right? So I will give you some examples, like some effort we make to kind of achieve such goal. So the first application or problem we're solving is actually the noisy image classification problem I just used as example, right? So suppose we want to analyze images which are not quite clean, but they can be non-ideals. For example, the image can be noisy. So how can we, for such cases, how should we kind of train a reliable classifier to analyze the image? Well, you have several options, right? I mean, first, you can directly analyze the image. For example, you can just train blindly a generic classifier to handle those noisy images. But the problem is that you may probably end up with some fragile deep learning methods, like I shared just now. If we just apply those, say, state-of-the-art classifier to classify noisy images, you may observe some degraded performance as the noise strength increases. So this will be not quite reliable and maybe not practical for dealing with real-world images. And if you think along the classic signal processing kind of a perspective, a very intuitive way of doing that is by first denoising and then analysis, right? I mean, this is very intuitive. If you want to handle some noisy signals, you first denoise it, and then once you have the denoise signals, you're going to analyze that. And in the image processing context, you can apply first an image restoration, like a network or algorithms, followed by a classifier. This sounds pretty intuitive, but the problem is that you may end up with some suboptimal, learning or some suboptimal models. So I mean, this is actually some lessons we want to learn from deep learning, because one of the good things for deep learning is that it enables end-to-end training so that you can actually directly optimize what you are truly interested of. Say if you are interested of classification, you should bring that part in the training of the denoiser as well. So this is actually the lesson we learn from both signal processing and deep learning. And eventually we come up with this solution that we do have two stage. We do have a denoising network, which is going to deal with those non-idealness. And we also have a module for, say, high-level computer vision, like classification or segmentation. But in the training stage, we're not following completely the signal processing kind of approach where we train this denoiser and this classifier separately, but instead we want to come up with an end-to-end training strategy where actually the total loss will be a hybrid version of all the losses which we're interested of. For example, we should incorporate both the reconstruction loss, which link to the denoising, and also maybe like a cross entropy loss, which link to your classification. And by having this joint loss, the whole algorithm becomes pretty robust and effective for task over the real world data. So we show some examples where we want to do a segmentation of images, but images with noise, no longer a clean image. I mean, the result for clean case will be very simple. Like normally you can get a pretty good result for segmentations, but if we are talking about a segmentation over noisy images, normally you're going to end up with some kind of misclassifications or kind of wrong classes in your segments. This is without considering any of the denoiser module involved. But by using the joint training and the hybrid loss, which we propose, we can end up with a much more robust kind of a segmentation or classifier when we deal with images with the presence of noise. So this shows that a combination of signal processing and deep learning can actually buy you something, which leads to a more practical solution for some of the computer vision problems. This is lesson one we learned. And also, when we try to kind of revisit like the convolutional neural networks or many of the popular architecture in deep learning, we realize that there may be some part missing there for example here in signal processing, we have kind of studied this for a long time. Like we should actually exploit image non-local similarities, not only in the local structures. So here I borrow the kind of illustration from the famous BM3D homepage, where actually the non-local similarity is a key ingredient for BM3D to be successful, right? Because for most of the natural images, you can easily search for some similar structures to kind of help you to process some local patches. You can actually go beyond the local filter rings, which kind of leads to a more effective result. But for kind of a convolutional neural networks, turns out that such type of convolutional-based method cannot generalize lots of non-local operations, and so that very important property of images, the self-similarity, has been ignored in those CN-based deep learning architecture. So by understanding this, we kind of revisit the deep learning kind of pipeline by borrowing some of the ideas from signal processing. So that we come up with this non-local recurrent network where we're kind of jumping all of the local filtering alone, but we also look at the neighborhood of some local structures. For example, if we want to process this local patch, we also look at the neighborhood where the local region may also contain some similar structures. But the way we do that is by coming up with a neural network layers which can exploit the correlation between the local patch and also the regional structures. And by having that correlation matrix, this kind of thing can help us to better process the local patch and come up with a more effective representation of that local kind of patch or local features. So So this kind of a non-local module will be some kind of complementary component to those local filterings used in the convolutional neural networks. And such architecture actually works pretty well for lots of inverse problems. We actually did a test on image denoising. And I think at the time when we submit the paper to NIPS 2018, we actually got a state-of-the-art result for denoising evaluated over some widely used data sets. Like here, I show example of the famous image Barbara. So by having this non-local recurrent network, we can do much better than either the classic method like BM3D and WNM, which only focus on non-local structures. Also some kind of CN-based method, which only focus on local structures. So we can do better than them by kind of borrowing the idea from both signal processing and deep learning. And also we try this for super resolution as well. Because even for super resolutions, you can actually kind of group those non-local patches and kind of better resolve those details, which in kind of benefit from this non-local similarity. And we give a try for some of the benchmark data set, and we can actually do better than some of the famous methods like MEMNet or DRN at the time. So this leads up to a more effective data modeling, which enjoys both the model flexibility and also the non-local modeling. That's actually the lesson 2 we learned by kind of borrowing idea from both. And the last lesson we learned is that, in fact, we can also explicitly combine a deep prior, which coming from external corpus, and also a good signal processing tool to better exploit internal image models. So what we tried is that we are using a kind of plug and play type of approaches, but there we are not using a single prior. We're using both priors from external corpus, which we train on neural networks, which are learned from external corpus, and we also use some internal priors. And in this case, we're using a WNM type of non-local low rank type of models to kind of jointly help us to denoise the image or reconstruct the image. And it turns out that it works pretty well. And I want to share some insights why combining the complementary prior can help in this case. Because when we deal with different type of images, sometimes the deep method can do better job, and sometimes the signal processing tool can do better job. For example, if we're talking about typical images, of course, most likely the deep method will win. In this case, we choose FFDNet, which is one of the best deep denoiser, kind of with public available implementations. It works better than those signal processing tools based on non-local similarities like BM3D or WNM. But this is not always true. If we're dealing with images with very strong structures, like images with lots of repeating patterns or like straight lines or edges, actually sometimes the signal processing tool can actually do better than deep learning because they explicitly exploit those structures like self-similarities or repeating patterns. And we show some examples that like methods like WM can do better than deep methods with like a fractional dB improvements. Another example is that when we deal with images from special modalities like MRI or like radar images, because maybe the training corpus of those deep learning method is not kind of sufficiently large, or sometimes there's a gap between the training corpus distributions and then the testing images, the deep method sometimes may fail and introduce lots of artifacts. Whereas the signal processing tools can do better because it's not really dependent on the external corpus. So all of these cases that we find, there are some kind of pro and cons between signal processing and deep learning. So the best way to make use both of them is to combine them and use them under a unifying framework. So that's exactly the reason why we want to kind of reconcile these two by using a plug and play approaches. And turns out that in all of the 3 cases, well, we can do a better job comparing to either the signal processing tool alone or the deep learning method alone. So this is a lesson 3 we learned. By showing these examples, I just want to kind of conclude that, yes, in fact, by better understanding the pros and cons of signal processing and maybe a more recent machine learning tools, there is a way that the old methods, the older machine learnings or signal processing tool can be somehow joining the advanced machine learning methods. And actually the combination of the both, or like the revisit of the deep learning method, can do even better job by learning the lessons or enjoy the advantages of both sides. So yeah, so that will be the end of the talk, and I hope this kind of experience can inspire you a little bit by thinking twice about advantages or limitations of different approaches, and eventually you can end up with a more effective algorithm. Okay, that's it. That's all for the presentation, and now I'm open for questions.
Thanks a lot for the great talk. And so we have this box Q&A that if you have any questions, you can put the questions in this box. So right now we have one question from Tony Zhang, which is, will the slides be available after the presentation? I think if the speaker can provide the slides afterwards, we will put it on the website.
Yeah, certainly. I'm going to share the slides, and also I think the recording will be live, and there will be a YouTube recording, right?
Yeah. Okay, so I saw one person raised a hand. Let me first go through the questions in the Q&A box. So Randy Ranau, do you want to ask the question in person? I can unmute you. Or if you don't want to ask the question in person, I will just mention the question. So in the image shown on the complementary priors with PNP, plug and play, slide, the brain image boundary conditions have critical information for medical applications, and the images did not appear to show substantive differences at the boundaries. Comments on how to work on the edges to get the necessary details. So maybe the question is how you can work on the edges to get the necessary details.
Yes, I think that's an excellent question. Yes, so I think for especially for medical image analysis, there are a lot of critical criteria in terms of to evaluate the quality, not only by looking at, let's say, PSNR or MSE, right? Those are kind of a general metrics for normal image quality assessment. But for medical image, I understand there are some special quality metrics. So yes, if we're talking about medical image analysis, we should impose a corresponding say either loss functions or maybe some kind of a regularizer which is specifically looking at those ages. So yes, specifically we can do that. But I think for this paper we didn't intend to really look into those medical image analysis. It's more about kind of come up with a general tool that we can combine two priors and show some improvement in general. We just use this as example because we want to show that for images for with special modalities, there are some cases that deep learning may fail. But I agree with you that if someone wants to work on the edges, we should, I mean, there are several approaches to do that. One is that you can impose a specific loss function, which try to look at those edges. For example, you can bias the high frequency component, or maybe use a loss function rather than PSNR. You can, I don't know, use SSIM or other metric, which kind of more sensitive to edges or high frequency component. Or you can either introduce some additional prior or regularizer based on, I don't know, some kind of a like medical image domain knowledge on top of, say, learning-based methods or kind of signal processing priors. All of these are possible. So I just want to answer that, this is a good suggestion. One can work on that. But unfortunately, for our paper, we didn't intend to kind of dig into that kind of part.
Okay. So for the next one, I go to the person who raised the hand. So Hassan, I will allow you to talk. So.
Thank you, Xixin. Good to see you again, Bihan. I
Hi,
just
Hunter.
had two questions, actually. One of them is about the complementary priors right now. You didn't mention exactly how you combine the two priors. That was one question. And then the other question is about the lack of robustness in deep learning models. You mentioned you have a denoising module at first, and then you pass that through the classifier. What if you were to provide noisy data in the training stage for those classifiers? Do you expect the network to perform as well as having a denoiser and then a classifier, or even better than that?
Mm-hmm. Great. I think both questions are really excellent. I mean, I thought about all of this. So let me share some of my thoughts here. So first, regarding this work is separate to ICIP. I didn't share the details because, time is limited, so I didn't share the details. But in principle, we kind of combine the two priors using ADMM type of algorithms, where you may have kind of two different regularizers, one coming from the external corpus. This is something like the normal plug and play. Use a deep image denoiser as the one of the prior. But on top of that, we have another term, which is not coming from deep denoiser, but coming from, say, a signal processing based denoiser. But you can still do this kind of variable splitting type of tricks using ADMM to kind of ends up with different iteration steps. So that's kind of a big picture of like how the two prior are combined. But I'm happy to share more about the exact form and algorithms. I can also forward you the paper if you're interested. But yeah, so that's roughly how the so-called hybrid plug and play works. Then regarding your second question, this is a really good point. We thought about this. Actually, this is the reason we have to convince ourselves why we want to do this. So the answer is yes. If you know what kind of noise you are dealing with, and if you believe that you maybe only deal with Gaussian noise or a specific type of noise, you can actually train a classifier which is specifically for Gaussian noise, and you can either fine-tune existing classifier with some additional data with Gaussian noise, but the generalizability of that model will not be quite good. Because say if say another day you're no longer dealing with Gaussian noise, if you are dealing with, I don't know, maybe Poisson noise or other type of corruptions, well, you have to retrain the model again, right? So this is actually a good thing for having a two-stage strategy here, because you don't have to replace the whole network. You can actually plug in a specific denoising network to deal with a specific noise. Or either you want, if you are dealing with some other corruptions like low resolution or blurry, you can also replace the denoising network with a, say, deblurring network. You kind of save some troubles and make the adaptivity better. I think that's kind of the whole motivation for this kind of approach. So
yeah, thank you.
Okay, thanks.
Okay, so next, I'm going back to the Q&A box. So by Scott Carey, do you want to ask in person? Otherwise, I would just mention the question. Okay, so let me just mention the question. So what kind of computational demands do your hybrid methods present? Oh, maybe.
So do you refer to the last one, the hybrid plug and play? Because there are several hybrid methods. Okay, so yeah, just in case you are talking about the hybrid plug and play, what kind of computational demands do hybrid present? Do you actually refer to like what kind of complexity or computational complexity? Is that the question? Okay, so I mean, in principle, see, this approach, well, I mean, we actually haven't kind of optimized from the perspective of computational complexity, but in general, this will be something similar to the normal plug and play, where you have to go several iterations for between, say, your applying the denoiser, and then you run the image update step. But there'll be one more step which you have to go through this signal processing step. Depends on what kind of signal processing tool we use. I mean, for this work, we use the weighted nuclear norm minimization approach. So there will be like additional step comparing to a regular, say, deep denoiser based plug and play method. So in terms of complexity, I think it really depends on what kind of signal processing tool we're using. For WNM, it's kind of scale roughly similar as like say BM3D or other non-local methods, where it pretty much scale as the number of pixels of images, and also maybe some size of the patch. But I'm not sure whether that's that answer the specific question here.
Yeah, so what I was really curious about is, are we saving computer time? Are we saving clock cycles by doing this? It's basically what you're doing is a pre-processing. You know, you're doing the traditional DSP method on the input, and then you hand it off to the deeper learning. And deep learning, you know, it's awesome, but it traditionally or it normally is associated with a lot of processing time and a lot of computational effort. So are we simplifying our task by doing this, or are we actually making it more complex because the deep learning doesn't change? It still requires a lot of processor power, but now we're adding another task at the input.
So yes, certainly I agree. So if you look at the so-called computational complexity, the deep learning, yes, it's actually well, much more complex if you don't have this kind of parallel computing things to speed up things up. So I think for this paper, we didn't intend to kind of improve the computational aspect. Yes, so you're right. It will somehow make things complicated. You have to run between several kind of tools or models. But I just want to show that, you know, regardless of these computational aspects, there are some kind of complementary part for what kind of information each model is modeling. There's something like the deep model cannot provide, and there's something like signal processing cannot provide. And actually, and to actually fully exploit the data structure or the data models, we have to take advantage of both parts. So I think that's kind of like the main message for this work.
Yeah.
But unfortunately, yes, it will be kind of more computationally expensive by combining the two. Yeah.
But at the same time, you're going to be getting intermediary steps and intermediary data points along the way. So it's not without cost, but it's also not without benefit along the way. Okay, great.
Thank you.
Okay, so next I will allow Ulbek to talk. Yeah. So.
Hey, Bihan.
Yeah.
Hi, Beck. Hey, Beck, how are you?
I'm very good. How are you? So I
great.
This question. So you presented basically several perspectives, which I appreciated. And then essentially when we move to this combination of deep learning and signal processing, essentially there are kind of two perspectives that I see commonly. One is this unrolling, examples EDM and net. And the second is plug and play, which is another one you talked about, right? Can you kind of give us your preferences and your thoughts about those two methods? So,
you mean unrolling and plug and play, right?
Yes, they're kind of related, but they're kind of different at the same time. So I want to just listen to your opinion about that.
Okay. I'm actually looking at more about their difference. So my understanding is this: unrolling. My understanding is that it's kind of like make a iterative algorithm deeper, because iterative algorithm, even though they can alternate between like two steps like multiple times, eventually you only use the last time, the last iterations. For example, if you're talking about E star, right? Even though you're kind of iteratively solve for various matrices, you only use the resultant matrices at the last iterations. But if you unroll it, you kind of relax this kind of condition. You use all of the intermediate so-called trained model, trained matrices, and the whole model becomes more flexible. So to me, I think unrolling is a way to two advantages. One is that we kind of scale up the model flexibility comparing to iterative algorithms. But even though we're solving the same problem, so that's the advantage one. And also by unrolling things, we can train the things end to end. This is something maybe an iterative algorithm is hard to obtain. For example, if you're talking about, say, sparse coding for denoising, normally you have to kind of set up several terms, like lots of proxies to kind of form your loss function. But if you unroll it, you can directly minimize the the MSE for the in the image level, so that this kind of a whole training process become an end-to-end kind of a framework. So that's like the two advantages to me if you are talking about unrolling, right? And plug and play, I agree. I mean, plug and play also have some kind of a way to make things more flexible. But my understanding is that actually, I mean, the unique thing plug and play provides is to kind of generalize a denoiser to maybe some specific type of inverse problem. It may not be only denoising. You can actually apply the denoiser for, I don't know, deblurring, super resolution, or compressed sensing. So that's the cool part, because you decouple the data model, which can be learned from a denoising process, with a specific imaging problem or a specific inverse problem, so that your trained denoiser becomes more generalizable. I mean, not only deep denoiser, but you can also use a signal processing based denoiser and generalize that to a specific inverse problem. So that's actually the kind of biggest advantage to me for applying a plug and play. Slightly different. I kind of maybe I see maybe only some aspects of either of them.
All right, cool, thanks.
Okay, thank you.
So the next one is by Peter Heller. So would you like to ask the question in person? So I already, yeah.
Yeah, sure. Thank you for an amazing talk.
Thank you.
And I think you already answered my original question, which was more details on how you integrate the signal processing methods with the deep learning methods, how you actually do the combining of them. But maybe, so I'd modify my question a little bit to ask how you measure the fragility or non-fragility of the result. Is it, is it just that certain classes of images the algorithm doesn't fall apart on, or is it via PSNR? How do you measure, after you've mollified the algorithm by combining some of the traditional methods with deep learning, how do you validate that, yes, it's less fragile?
I think there are different kind of evaluation metrics, depends on which kind of aspect you're trying to improve, right? I mean, yes, for most of the image restoration problems we're kind of dealing with, MSE, PSR, those are important metric we're trying to use to evaluate the the effectiveness of the combinations. But those may not be the only metric. Like, for example, I show some example that we also look at the robustness, say how robust maybe a combined version can do with the presence of noise, or with I don't know, with some non-idealness in the data. So it really depends on what kind of aspect you are looking for. But some of the things you mentioned are some of the metrics we definitely need to look at. Also depends on the applications, right?
Yeah.
So I'm not sure whether that answered your question or.
Yeah, I think you did. Yeah, thank you so much.
Okay, thank you.
Okay. So the next one is a follow-up question by Scott. So Scott, do you want to continue with the question on computational demand?
I think we actually discussed that already
Yes.
when we were addressing the first question. Thank you, though.
Okay.
Thank you.
Okay, so then the next question is by Venkat. So Venkat, do you want to ask the question in person?
Sure. Might have come for this Bihan. Very interesting talk. So the question was about the hybrid approaches as well. And sorry if you answered it already. But when you showed these different classes of images, right? From what I understand in that work, this approach was it worked well across a class of images. Text seems like text type of images, MRI, and then did you have to do a lot of tweaking with, like, not a lot, did you have to tweak the parameters of the relative weight between the different priors, or was there relative stability? Of course, we all adjust the parameters, but was there some way, like if you had a system like this, to choose, hey, the class of images that you're getting used to be from MRI versus text images? It's a question about the adjustment of parameters across the classes.
Oh, okay. So first, I think the voice, Venkat's voice, is a little bit soft. I'm not sure whether I get the question correct, but by reading the question you're leaving in the Q&A, I think you're talking about whether there's a lot of like parameter tunings for this kind of a hybrid approach, right? To kind of is it like a task specific, or do I need to come up with a different kind of parameters for different modalities or different images? Is that the question?
That's
Sorry,
right.
I think the volume is a bit low. I cannot hear very clearly.
That's right, Bihan. You're right.
Oh, Okay, so yeah, to answer that question, I think we did some tuning, but we don't actually tune each individual images or each different modalities. So there will be like a one set of, say, weighting in the loss function, which will be consistent for different images or different modalities. But you're right. I mean, for us, there is no like a very systematic way or automatic way to come up with those weights. So one have to tune that, unfortunately. And I think that's a common problem for lots of optimization-based methods. I mean, recently we're looking at some of the approaches where one can use a reinforcement learning to kind of somehow automatically tune those weights in the loss function. So I think that could be a promising approach to go. But unfortunately, we didn't kind of discuss this in this work. But I mean, if you're interested, I can link you to some of the recent papers for these aspects.
Got it. Thank you. Thank you.
Thank you. Thank you, Venkat.
Okay, so the next one is by Randy. So Randy, I think you can, if you want to raise the question in person, you can just unmute yourself. Or I can go through the question. So the question is, wavelets may be an optimal approach in this specific application. Thoughts? It is not very clear which one you are referring to, or
So it depends on what you mean by optimal approach. So, I mean, we just showed that in terms of sparsification. If you want to sparsify a signals, those analytical transform may not be, optimal. But it's possible that for some applications, wavelets turns out to be somehow the best choice. It depends on your kind of what do you mean by optimalities or what type of problems you are looking at, I think.
Okay. So the next one is by anonymous attendee. So your presentation details with images, do you try these ideas on temporal signals such as sounds or measurements from another time-dependent process?
Oh, okay, good question. In fact, yes. I mean, we have some tools of like, for example, online transform learning method, which enable us to deal with temporally changing signals. I mean, we show one example of video denoising where actually the learn transform can evolve as a new frame arises. So it's not like static transform. The transform will kind of change as new frame arise. So yes, one can actually apply this to other type of temporal signals. Like I think some of the example, these anonymous attendee mentioned, like sounds or like acoustic signals. One can do that. But I mean, the reason I didn't do that is because, I mean, personally, I'm working with images, so definitely I just try something I'm familiar with, and also I think acoustic signals or sounds may have less spatial resolutions, whereas the most of the transform or like convolutional neural network have to exploit those spatial structures. So I'm not sure like whether we will get such a surprising effectiveness, but in principle, yes, you can apply them to other type of temporal signals. But we haven't tried this.
Okay, so the next one is still anonymous attendee from, which is the best deep learning method for classification of medical images?
Okay, I think this field develops really fast. It's actually after every major conference, the so-called the best method may change. So I cannot say this for sure. But I know, like for example, UNet has been widely used for medical image analysis, such as CT image analysis, tumor detection. So it really depends. You have to specify what are the medical images we are talking about. What are the modalities? And there could be different so-called state-of-the-art methods. So my answer is it depends. And also you should look at, say, after every major conference, you have to kind of recheck those answers.
Okay. So the next one is due by Randy. So it says, very subtle contrast is keenly important. So perhaps a follow-up opportunity.
So contrast is important.
So Randy, do you want to clarify your comments or question? Okay, so maybe Bihan, you can comment a little bit on this.
Actually, I didn't quite get the question, but my understanding is this: you're talking about, say, for some applications, perhaps the subtle contrast is important. Like you have to preserve those subtle contrast, so that maybe this kind of subtle contrast may tell you something important. For example, for some important structure detection. So yes, I mean, like I mentioned, we didn't look at some specific applications where such kind of need is necessary. But if we have well-defined problems where we know those are the say contrast is something you're looking for, one should come up with a corresponding loss function or some kind of regularizer to enforce those information to be preserved in your reconstruction or in your analysis. So a follow-up, yes. I mean, definitely we can apply this to a specific problem or specific application, and to kind of further preserve the subtle contrast.
Okay, so so the next one is by the anonymous attendee. Is there any reason why deep learning-based approaches are more widely used with 2D signals than 1D signals?
Well, I would say maybe different people have different answers. But my own opinion is that no matter it's deep learning or as long as it's a learning-based method, the key ingredient is to exploit the correlations. I mean, if you have a really high dimensional data, there's more opportunities to exploit kind of more significant correlations for the image. So this actually explains like why you see a much more improvement for, say, image processing applications or even video or tensor kind of a modeling method by running this CNN type of algorithms or deep learning algorithms, because it gives you kind of more information to exploit. Rather than, say, if it's a 1D signal, perhaps the correlation just in that one dimension, so that the additional information you can get from the learning may be less. I think that's like a pretty high level answer, but different people have different opinions. I don't think there's a unique answer to this question.
Okay, so the next one is by Scott. Does using a simpler DSP strategy first make it easier?
Yeah, so it depends on what do you mean by make it easier. So I mean, I don't think the sequence here actually matters, but I mean, it depends on what kind of aspect you're talking about. Say, if you're talking about the computational aspect, yes, I think normally we don't want to get into those complicated models, right? But I mean, the key message I want to kind of actually convey here is not in terms of a computational aspect. It's actually in terms of how effective the DSP-based models or deep learning model can be, and whether there's still some space where one can be complementary to each other. So in that sense, I'm not sure whether this kind of a sequence really will be that important. The more important thing is we have to kind of combine the right pairs of DSP tools and the deep learning tools. Yeah, so to answer your question, it really depends on what kind of aspect you are talking about and what do you mean by make it easier.
Absolutely. And, this also comes back to, I think we already touched on this when we addressed my first question, but I fixate on computational time, mainly because it directly relates to what I do professionally. So that's why my questions come back to that. But I can also see there is definitely space for finding the right combination and finding and aiming for higher accuracy and higher performance.
Agree.
Thank you very much.
Thank you, Scott.
Okay, so the next one is by Nitin. So let me first find her.
Oh, okay.
Yeah, so the question is, in general, are hybrid learning methods as data demanding as conventional deep learning methods?
I mean, good question. So I think we talk about this data efficiency or data efficient or data inefficient problems when we compare the so-called signal processing and deep learning, right? So if we are talking about the very generic deep learning models, it's really data consuming. You have to kind of feed them with a relatively larger scale of data. So that in that case, it's more data demanding. So having a hybrid learning method, for example, like for the like hybrid, I don't know, hybrid plug and play with some methods. In fact, I think it will kind of leverage more on this kind of intrinsic structure or internal image models rather than only relying on the external corpus. So in that sense, yeah, perhaps it will be less data demanding. For example, for plug and play, like just now Ulla Beck mentioned, one of the unique properties that it can generalize a denoiser, a specific denoiser to more diverse inverse problems. In that sense, you don't have to kind of retrain different models for different problems. So in that case, it will be less data demanding. It kind of help you to generalize one problem to other problems. And also by having this DSP model plus a deep model, the signal processing model will introduce some kind of prior or understanding of the data, which kind of reduce the load of data demanding by only using the deep model. So in that sense, I think in general it will be less data demanding comparing to like a generic say CNN type of network.
Okay, so so the next question is from anonymous attendee. So for data involving motion patterns analysis like visual odometry, would your algorithm be able to potentially and dramatically improve its performance via reducing potentially redundant key points that can be considered as noise? Because so far your data set involves images, videos, and I was wondering if a similar approach can be applied to the motion pattern data set.
Okay, good question. Personally, I haven't really deal with this data as well. I mean, I'm not familiar with the video odometry, but I think potentially yes. Considering my guess is this: your motion pattern data set will also have those temporal correlations within this data set, so that perhaps online learning methods or good models for handling those spatial temporal data or even volumetric data can apply there. But to be honest, I haven't tried this. I can only say that potentially this is doable, but whether it's promising, we have to give it a try. So so I don't think I'm in a good position to comment on that actually.
Okay. So next one is by Arindam. So Arindam, I think I allowed you to speak. So if you want to talk about the question yourself, you can also just.
Yes, I have the question. I am audible, right?
Yeah, yeah.
Okay.
Go ahead.
Yes.
So the image that Bihan shown, that the butterfly image with non-local non-local what else say recurrent network, how it is different from a self-attention network? Because I see some of the part related self learning means the model is integrated with the recurrent neural network, or it is a separate model. Then a recurrent network is added. What is actually how it is done? Yes.
Yes, I mean, good question. In fact, yes, there's a really close connection to self-attention. In fact, I think self-attention was first introduced, first in the NLP type of applications, and later people use that for computer vision task. And actually, the very first non-local network is introduced by Xiaolong Wang and some other authors, where they also do this for video analytics. But at the time, they didn't really, it's not quite clear how the two are related. But turns out that they are very similar. But for our non-local recurrent networks, I would say there are two major, not major, but two possible difference between the self-attention. First is that, dealing with low-level vision problems like image restorations or imaging problems is slightly different than high-level vision problems like analytics or classification, because, for example, take an example of denoising, probably it's not a good idea to relate a local patch to the whole image. because really, if you look at the whole image, the noise itself in the image will kind of give you some wrong correlation calculation, which may not kind of buy you something, but actually degrade the performance by affecting the accuracy of the correlation matrix. So this is actually a major difference, because high-level vision probably don't have these issues because the image is actually clean. For noisy images, we have to purposely limit the size of the neighborhood to not the whole image, but the regional kind of a limited region, but not only in the local patch, slightly broader, so that we enjoy the self-similarity in this region, but also be relatively robust to noise or other type of corruption, which avoid those possibly overfitting in learning this correlation matrix. I think that's the major difference difference one. And also, if you look at the embedding process, so all of this embedding are necessary, because in the very first layer of this non-local network, you have to deal with image patches. So the embedding is necessary. Otherwise, this will be like a pixel level type of correlation, which doesn't really make sense. But for self-attention, I don't think this is a necessary step. They can actually work directly with features. So yeah, I mean, but I agree with you. It's a very similar idea to self-attention, in fact. But if you consider these two, difference, is slightly different.
So you just want to say that it is more like a part level thing, that a little bit more like a part level thing, part based model, something like that.
What do you mean by part level?
Part means a little bigger than the patch level, something like that, in some sense.
No, I mean, so all of them are. I mean, the purpose of this non-local model is to kind of have a better modeling for the patch, but the self-attention mechanisms always link local features to the whole image. But this is not quite effective when we talk about image restoration, because we're talking about input image with noise. And if you relate the local patch to the whole image, those noise will affect the accuracy of this correlation matrix construction. So based on that, we purposely limit not the local patch. Still, we're modeling local patch, but when we try to calculate the correlation matrix, we're not correlating the patch with the whole image. We only correlate the patch with the local. I mean, not the local, but the regional neighborhood. I think that's the kind of the one of the difference if you're talking about comparison between to self-attention.
Okay. Thank you very much. Nice talk.
Okay, thank you. Right. I mean, yeah, thanks.
Okay, so the next one is by anonymous attendee. How could you apply the signal processing and sparse methods to semi-supervised learning or unsupervised learning?
Okay, good question. In fact, if we're talking about like signal processing or sparse method, for example, the transform learning method we Sai and I work on for a while, like the MRI. I use this as example. In fact, this is not a supervised method. It's a completely self-supervised method, meaning that we're not learning the transform from external corpus. We are learning the transform directly from those undersampled case-based measurement. So this is actually following a so-called blind compressed sensing pipeline, where you jointly reconstruct images while refining your transform. So actually, that's one of the advantage if you compare those kind of shallow type of sparse coding method to deep methods. So yes, we can actually. I mean, it's actually the fact that we follow the unsupervised learning approach to construct those sparsifying transform or dictionary. So unlike the deep learning. And I think most of the other signal processing type of tools without too flexible models, it's much easier to make it unsupervised or semi-supervised. So yeah, so I don't know what you mean by apply, but in fact, these are unsupervised approaches already.
Okay. So the next one is by Vamsi. So I already allowed Vamsi to speak. So if you want to post a question yourself, you can just unmute yourself. Or I can go ahead and talk about the question. Okay.
Images representation. Model structure.
Okay, so let me go through the question. So how far the input image representation affects the model architecture? What are the best possible representations of images for denoising and super resolution applications?
Okay, so let me answer the second question first, because I'm not quite sure about the first question. So the second question is what are the best possible representation for denoising and super resolution? In fact, there are no so-called best possible representation, because when we talk about representation, we're talking about a good model for natural images, and there is no so-called true model for natural images, because you cannot really come up with some mathematical rule to describe like natural images. It's unlike your Gaussian noise or other type of statistically kind of describable type of thing. But for natural images, you can only get a better one by kind of introducing more priors or introducing more flexibility in your learning process. So I don't think there's something called the best possible representation. So the actual good representation will also depends on what data you are dealing with and what kind of applications you are solving for. So it will be really depends, I would say, to answer that question. And the first question, I'm not sure whether I get it, but so are you saying that like what type? So are you saying that if the image representation will affect the model? I mean, in fact, the model or the architecture, so the neural network architecture are actually for image representation, right? Because once you have a good models or a good architecture, you can come up with a more effective representation. I mean, nowadays it's not like the old times where people use handcrafted features for, say, SVM or some methods. Actually, the whole model itself will play the role of image representation already. So I didn't quite get it, but feel free to comment if you mean otherwise.
Okay, so if there's no follow-up questions, so I will continue with the last question. So the last one is by anonymous attendee. So can you please briefly explain what is transform learning?
Oh, sure. So yeah, this is a long story. Like we did a lot of spend many years working on that. So pretty much like I explained here, in the high level, transform learning is just to we try to optimize the transform so that for a particular image or any data you are interested, the transform can be further updated or further optimized so that it gives you even sparser representation. Right. It's just like you can formulate everything in terms of a loss function, where the loss function composed of, say, sparsification errors or a sparsity imposing norm like L0 norm for this representation. But yeah, I skip those details because it's a long story. I think Sai covered part of this transform learning idea in his talk several weeks ago. But if you're interested, you can actually, we actually have a project website, Sai and I maintained, which has a collection of all the transform learning papers. So you can just search, say, transform learning, or maybe my name, they come up with the project website, and you can dig into that. But or you can actually refer to Sai's presentation or talks several weeks ago, with more details. But in general, it's a machine learning algorithm to further optimize the transform so that it gives you a better or sparser representation of the images you are interested of. That's a one-sentence summary of what transform learning is.
Okay, so
all right.
Yeah, so that is the last question. So let's thank the speaker again for the wonderful talk. And the next talk will be on November the 3rd. It will be given by Professor Nicole Seiberlich from University of Michigan. Yeah, so we will see you in 2 weeks.
Okay. All right. Thank you.
Thanks.
Thank you, Jim. Okay, bye-bye.
Bye.
Recording. Okay.